Hey guys, welcome back to quantum mechanics. Hope everybody had a good weekend, and hope you're ready to do some time-dependent perturbation theory. So that's what we're going to shift to now. So everything we've done previous to this is assume that there's been no time dependence. But as we're going to see, time dependence is an important case, and in fact, it'll lead us right into scattering theory, because you can treat scattering as kind of a special case of time-dependent perturbation theory, as we'll see. Okay, so I'm just going to start with a kind of a quick overview, kind of get the big picture, kind of get some general formalism down. I'll talk about, and we'll discuss one simple example, and then next time we'll pick it up with some more difficult or more, more involved problems. Okay, so just here's some general statements. So in general, time-dependent perturbation theory, and I'll go ahead and apologize for the quality of this of my notes here. That it gets a little better in a few pages. It's just kind of have to deal with it for right now. So time-dependent perturbation theory is basically designed to deal with situations where you have some system that's in an unperturbed state, say, that we would call like H0, like before. And then at some point, a perturbation gets turned on, right? And this can happen in several different ways. It can be like a sudden thing that happens, like where you flip a switch, or it can be some adiabatic type of turning on, like the ramping up of a potential or something like that. It could be sinusoidal, right? A lot of you guys have probably dealt with experiments where you have some electric or magnetic field that's fluctuating in a sinusoidal way. And so the main question that we try to ask is, say you start, initially in some state, just call it N, right? And then you have in an unperturbed system, and then you turn the perturbation on, and then you turn the perturbation off, right? And the question that we're going to try to ask or try to answer is, what's the probability that after some time t, the state has made a transition to another state? Okay, so that's the main question or problem that you're trying to solve when you do time-dependent perturbation theory. Okay, so we'll still assume that the total Hamiltonian, even when the perturbation is of a kind of a separable form, right? So that the total Hamiltonian is going to consist of a simple piece, so that's the unperturbed piece, and the time-dependent piece now is going to be our perturbation, and it's still small, but the difference is now that this thing is going to be dependent on time. Okay, and we're going to assume, for simplicity, that all the time dependence, as far as the Hamiltonian goes, is coming from the perturbation part. And so again, H1, or H prime, the perturbation Hamiltonian, is small enough that we're assuming we can use a perturbative expansion. All right. So we know that from last semester that state kets evolve with time. Even in the absence of a Hamiltonian that depends on time, right? If you go back and look at our time evolution discussion about time evolution and stuff like that. So some general state N at a later time t is going to be some eigenket, right, times some time dependence. It looks like e to the minus iet, right, something like that. Okay, so that's going to be so we're going to have time evolution there, but we're also going to have some time dependence coming from the perturbation, and we're assuming again that this guy satisfies the normal eigenvalue type of equation. The main difference really is that a lot of times in time-dependent perturbation theory, we'll rewrite the energy in terms of h bar omega, because many times we're dealing with sinusoidal types of potentials, or periodic potentials, and so a lot of times it makes more sense to talk about frequencies instead of energies. Okay, so let's say we start with some general state alpha, right? And or we want to ask, what does this some general state alpha look like at some later time t, given that these states evolve with this type of time evolution. Okay, so we're working in the Heisenberg picture, right? The Heisenberg picture where the eigencats evolve with time. And that's typically the case, okay, where we will work in the Heisenberg picture. So at some later time t, we could be in some superposition of these states, right? And so we can always rewrite our general state alpha that now is going to depend on time as kind of a linear combination of these eigencats and times some coefficients, right? And then I could also just rewrite this in terms of the time independent piece and pull out this exponential. So when we studied quantum dynamics, back when we were talking about time evolution and things like that, we showed that the probability, if you're interested in doing a measurement for a system that's in some particular state, is just given by these coefficients squared, right? And the time dependence shows up in these coefficients. So like I was saying in the beginning, our goal in time-dependent perturbation theory is to actually calculate these coefficients, not only in the case where you have just normal time evolution, but where you have some time dependence coming from the perturbation Hamiltonian. Okay, so let's talk about how we do this in a perturbative way, okay? We're going to start with the time-dependent Schrodinger equation, okay? And so that means I'm going to have the time derivative part on the left-hand side. On the right-hand side, I've got the Hamiltonian piece, right? And the Hamiltonian I've broken into unperturbed plus the perturbed piece. Okay, and so the next step is to take my state alpha and plug in the linear expansion. All right, and I want to try to get rid of, so I've got over here, I've got these operators, right? So I want to try to get rid of them. So I'm going to hit them from the left with another eigenstate of our unperturbed Hamiltonian. So let's focus on this left-hand side. Okay, so the left-hand side, here's the ket or the bra that I just brought in. I've got this time derivative, and then I've got this expansion, right? But remember, I can't just take this derivative of just this piece because there's some time dependence in this ket. So I can rewrite it in terms of the time independent part and the time dependent part, right? And now when I take this derivative, it's going to be chain rule, or no, not chain rule, but just a derivative of two things that are being multiplied. I don't remember what the name of it is. So you can take a derivative here, right? And that's going to give me this c dot, okay? And then I also have the piece where I take the derivative of this thing, and that gives me this second term, the h bar omega piece. Okay, so that's where this omega is coming from, is from that derivative. And then I can write, once I do that, I can write this state, the state that we multiplied by, which also has time dependence. I can pull out that time dependence, and then at that point we can use the orthonormality of these kets, these Brownian kets, the energy eigenkets, right? And so in the end, the left-hand side just reduces to IH bar. This is the derivative of C with the subscript F with respect to time, and then plus the energy, the final energy times this coefficient at F, right? Because I've replaced H bar omega with F here. Okay, so you notice that I'm using this Kronecker delta function when I collapse these things to pick out the terms in the sum where n is equal to F. Okay, so on the right-hand side of our Schrodinger equation, so go back here. So here's our right-hand side, and we're hitting it from the left with this eigenbra F. And so I have the sandwich of these bra and ket with these operators. Right, this guy, I know I can operate to the left, and it just gives me EF times a CF, because what happens is, again, we use we pull out the time dependence of this bra, and the product's going to give me just the factor of CF left over. And what we have that we don't know how to exactly compute yet is the matrix element of the perturbation, right? And you can see here I've combined the time dependence coming from the initial ket with the time dependence of the final ket. And I'm not sure that I write it here, but WFN is, or omega FN is just the difference in omega F and omega N. So it's omega F minus omega N. Okay, so I can put the left and right-hand sides together of the Schrodinger equation. And so let's see what I have. So here's the left-hand side. Here's what I have on the right-hand side. And you can see what happens is the EF times CF terms are going to cancel. And what I have left is a differential equation for these coefficients, right? And what you see is that the coefficient F depends on all the other coefficients, all right? So in general, there's an infinite sequence of coupled equations, okay? So that means that the ith coefficient is going to depend on the jth and the kth coefficients, okay? So that's a tough situation to deal with. All right, so you can't. It's difficult to solve. Ideally, we would like to solve for these coefficients exactly, but the fact that they're coupled equations and there's an infinite number of them makes the problem hard, to say the least. Okay, but the thing you do note is that as h1 goes to 0, so as we turn the perturbation off, we find that this derivative has to vanish for all coefficients. Okay. So what we're going to do is we're going to assume that this guy is small. Okay. So if the perturbation Hamiltonian is small, then we can hope that we can look for perturbative solutions, right? And if we're interested in solving for these coefficients, we can look for perturbative expansions for these coefficients. So just like we did before when we expanded in the eigenvalues and the eigenkets, here we can expand these coefficients. All right, so I'll have a 0th order part to the coefficient, a first order part, and first order meaning it's a first order in the perturbation, second order, and so on and so forth. All right. So now let me take this expansion and plug it into our equation that I have here in the box, okay? And I'm going to use some shorthand notation, so I'm going to write this as H sub F, or maybe I changed the notation to M here, yeah. So this thing is just the this piece here where I've replaced F with M, okay? So I'm going to plug my perturbative expansion for these coefficients in. All right, and so you can see I have the derivatives here, and on the right-hand side, I just have the coefficients. Okay, so now we have this kind of, this infinite number of equations. So what we can do is group by powers of H1, right? So at 0th order, here we've got this guy on the left-hand side. On the right-hand side, we don't have any 0th order pieces, right? Because this 0th order coefficient is being multiplied by this Hamiltonian, which is first order, right? So the 0th order term just tells me that CF is a constant, right? And then I can go on and match the first order term. So the first order term would be this guy on the right-hand side, or left-hand side, and this guy on the right-hand side. So it'd be the 0th order coefficient multiplying the H1. Right, and you can see that what happens is you can basically start to bootstrap your way up. So we start at 0th order, plug in 0th order here, we can solve for the first order, and so on and so forth. Okay, so that'll be our general approach. Yeah, they are, what does that say? Note that the leading order equations indicates they are all, yeah. So that's just saying that these things are constant in time, which is what I was saying before. Okay, so let's consider now this is a situation where, so let's say we have a situation where we set up our system So it's at t equals 0, the system's in some state, and we'll specify that state to be I, so little I naught. So in other words, our coefficient, the time independent coefficient, or I should say, our coefficient at t equals 0, where of the f state is a delta fi. So in other words, it's 0 unless f is equal to I. Right? And what we want to try to find is our coefficient at some later time t. In other words, what's the amplitude that we find our state and our system in state f, given that we started in state I. Okay, so we go back to our equations, right, and to zeroth order. At zeroth order, we start with this guy. Okay, and what we know is that the derivative is 0, right? But we have our initial condition. Okay, so we know we're in the ith state, and we also can write down the first order equation. Right, so we have this guy, and we know what the initial state is. Right, so this initial coefficient here, the guy that goes into here, is a delta function, so it picks out just one term out of this sum. Okay, and so we have this situation here. So we've got the first order coefficient being proportional to this matrix element, right? So two unperturbed states being sandwiched around the perturbation Hamiltonian, along with this time-dependent piece, right? And so what we can do is we can solve this as a differential equation, right? And we can solve it by just separating and integrating, and then using our initial condition, which was that we know we're starting in this ith state, right? So the initial condition is a delta function. So that's what I'm doing here. So I separate and I integrate with respect to time, right? And so you can see that this coefficient is so this would be our zeroth order term, right? So this is the delta function, and this would be our first order term, okay? And so what we'd have to do is, if we wanted to compute this coefficient to first order, we'd have to know what the form of the perturbation Hamiltonian is. But once we have that, we can plug it in, evaluate this matrix element, and do the integration. And it's just as easy as that, okay? All right, so if we have, so now that you compute CF1, and now, like I was saying, you can kind of bootstrap your way. You can build your way up to higher orders, right? You can plug this coefficient into the second order equation, and you keep going until just like we did before. You would keep computing coefficients until you'd see that you were converging on an answer. Okay. And so that's actually the approach that most undergraduate books take. Okay, and maybe you've seen this type of approach before. We're going to do things a little differently and use a more kind of compact scheme for calculating these transition amplitudes to any desired order. And the reason I'm going to do this is because it's going to set us up for scattering theory. So it's going to introduce some notation that's going to make studying scattering theory a little easier. Okay, but we'll put that off. We'll wait until next time, or at least later, to do that. First, what I want to do is try to apply what we've learned so far to just a simple problem. Okay, so what we're going to do is we're going to consider a one-dimensional simple harmonic oscillator. All right, and we're going to start in the ground state. So initially we're in the ground state, and we know what the unperturbed Hamiltonian is. And we're going to set the initial time to be minus infinity. Okay, and so this is going to seem a little strange, but it makes sense because, compared to, so the idea is that, you start at some, time, and then you end at some time. And the perturbation Hamiltonian only acts for a very small amount of time, right? So it's equivalent. You can set the initial state to minus infinity and the final time to plus infinity, and it doesn't really affect anything, but it simplifies the analysis. And we'll get more into this later on. But for this case, just let's assume that we can do this. And it'll make the integration a lot easier. Okay, But like I said, taking this limit is a natural thing to do when you're studying time-dependent perturbation theory. Okay, so we've got a simple harmonic oscillator, and we're going to apply a perturbation to it that is going to look like this. All right, so this is E here is an electric field. Okay, so we've got basically like a charged particle on a spring, maybe, and this Hamiltonian goes like the electric field, the position operator, and it's exponentially decaying. Okay, so tau here would be like the natural length or time. What's the word I'm looking for? The time interval, right? Or the lifetime, I guess you would say, of this perturbation. Okay, so the important thing is this is what our perturbation looks like, and if we want to compute the probability that we end up in some other state, let's call it n, right? Because remember we're starting initially in the ground state. We want to compute the probability that at some later time, but much later time at plus infinity, what's the probability that we find the state or the system in state n? Okay, so what we can do is we can go back and so we know at zeroth order it's going to be 0, right? Because the delta function would be delta n 0, and that's just 0. Unless n 0, that's not what we're looking for. We're looking for a different state other than the ground state. So our first contribution is going to come from the first order term here. All right, so we want to plug in our Hamiltonian into our perturbation Hamiltonian into our formula. Okay, and so what I'm going to do is rewrite x in terms of a and a dagger. A, when it hits the ground state, it's going to give me 0. A dagger will raise it to 1, right? And I'll get a non-zero contribution if n here is the first excited state. Okay, so that's what I've done. I've used, here's the delta function right here. Right, and so what that does is it sets all the n's to 1, right? So here omega sub n0 is now omega sub 1 0. Okay, so this is the difference between the first excited state and the ground state energies. Okay, so once I do that, what I'm left with are just some time-dependent exponentials, and when I see this exponential that goes like t prime squared, and another exponential that goes like t prime linear, that's kind of telling me that maybe the best way to evaluate this, besides plugging it into a computer, would be to try to complete the square in the exponentials. And so that's what I do. So I'm going to complete the square here. So I'm going to rewrite this term. First I have to pull out a tau squared, but then I can add, subtract half of this term squared, right? So I'm just completing the square. And so that'll give me this term that's a perfect square, minus this thing that doesn't depend on t prime, right? So I'll be able to pull that out of the interval. So I get this times this stuff. Okay, so that means that when I go back and I plug in this thing in the integral, that I get this exponential piece that comes out in front, and all I need to do is take the integral of this thing, right? But now I can actually do this by hand, and I must have been well, I guess I just wanted to show you guys that I can actually do some calculus every once in a while. So here I'm making a substitution. I'm just replacing all this junk inside the exponential with some new variable u, and so that gives me a simple integral to do. It's just a Gaussian integral, and so I can look that up in a book, right? And what I find is that C1 looks something like this. Okay. So that means that the probability, so you can see what happens. So the reason that we took t to minus initial to minus infinity, t final to plus infinity, is that so we can get something here that doesn't really depend on time. So it's much later time, and the time dependence is dropped out, basically because it's an exponentially decaying perturbation. So we can say now that the probability for for a ground state to first excited state transition is just this coefficient squared. Right, so I can just plug this stuff in and square it and simplify, and I get something that looks like this. Okay, so depending on that tau, the value of tau, that'll tell us what the probability of the transition would be. Okay, so that's all I have for today. And when, like I said, when we pick it up next time, I'll start to talk about this other formalism that we'll use that'll kind of set us up for perturbation theory. Okay, so I think I did put a homework assignment in the Dropbox, and if you guys have any questions about that, you're always free to shoot me questions. And I think I promised you guys that I would grade your homework, and I didn't. So I'll do that. I'll get it to you in the next day or two. All right. But I'm sure everybody's doing fine, and so you don't need to worry about it. But I'll talk to you on Wednesday. All right. Have a good week. Bye.